Near-Earth objects. Objects that come close to Earth, or in scientific terms, asteroids and comets. The worry is that one of these may be on a collision course with our planet. Fortunately, it's a very small chance. But scientists believe that dinosaurs became extinct because of the collision of a large asteroid 65 million years ago with Earth. In this episode, we are going to explore meteors and asteroids, what happens when they fall to Earth, and the possibility of a disaster if a big enough one impacts our planet. We start our explorations of asteroids and meteors in a small Russian town called Chelyabinsk in the year 2013. The morning of February 15th was disrupted by a fireball streaking through the sky. This was followed by a bright flash and a cloud of dust and gas. Some people felt intense heat. They reported seeing a huge line of smoke in the sky. Windows burst in buildings across 6 Russian cities in the region. Almost 1,500 people were injured, mainly from flying glass. What caused all this? It was near-Earth asteroid that entered the atmosphere. There was whole-scale panic since the event was not predicted.
It was moving with a velocity of about 24 kilometers per second, and therefore it was moving much faster than the sound, and the shock wave created, it completely sort of shattered the window panes, and many inhabitants of Chelyabinsk, they got hurt.
We now know that the meteor was approximately 17 to 20 meters in size. It exploded at a height of 15 to 20 kilometers above Earth, releasing 500 kilotons of energy. Just to give you an idea, this is approximately 30 times greater than the energy released by the atomic bomb over Hiroshima. It is equivalent to about 500 kilotons of TNT. This explosion was so enormous that it was detected in monitoring stations as far as Antarctica. Post the explosion, about 5 tons of meteoric material reached the ground, including a 650 kilogram meteorite that was recovered by divers from the bottom of a lake called Chebarkul in Russia. What this incident shows us is how important it is to monitor small bodies in space that could pose a threat to Earth. Before we see how this happens, let us understand what meteors and asteroids are. When we travel into space, we encounter a host of heavenly bodies. Now, asteroids are rocky masses like planets that orbit the Sun, but they are too small to be classified as planets. Most of them are found in the asteroid belt, a ring which lies between the orbits of Mars and Jupiter. It is believed that asteroids are debris left over at the formation of the solar system about 460 crore years ago. There was a huge interstellar concentration of gas and dust, much of which coalesced together to form the Sun. Some of the condensing dust in the cloud became planets. The objects in the asteroid belt never had the chance to be incorporated into any of the planets. Now, some of the pieces can be very large, others can be tiny, as small as a grain of sand. Because of their smaller size, asteroids lack the gravitational pull to shape themselves into a sphere, meaning they usually have a rocky, irregular appearance.
There are many smaller bodies, maybe whatever left over from the formation of solar system. So out of those smaller bodies, there are comets which are distinct. Objects like asteroids, let's say, are also similar to these cometary bodies, but they've lost more of these volatiles, and so they are just essentially smaller rocky mineral bodies and generally irregular in shape.
Now, meteoroids are small particles from an asteroid or heavenly bodies like comets. Their size can range from about a fraction of a gram, that's the size of a pebble, to 100 kilograms or more, which is the size of a huge, life-destroying boulder. When these meteoroids enter the Earth's atmosphere, it burns up and turns into a meteor or shooting star. And if the particle is large enough to survive its trip through the atmosphere and fall to the ground, it becomes a meteorite. Now, this can cause potentially huge damage depending on the size. About once a year, an automobile-sized asteroid hits Earth's atmosphere, creates an impressive fireball, but burns up before reaching the surface. Every 2,000 years or so, a meteoroid the size of a football field will hit the Earth and will cause significant damage to the area. And only once every few million years, an object large enough to threaten Earth's civilization comes along. Impact craters on Earth, the Moon, and other planetary bodies are evidence of these occurrences. Understanding asteroids has become so relevant for us that in December 2016, the United Nations General Assembly decided that 30th June would be observed as an International Asteroid Day. June 30th is the anniversary of the largest asteroid impact in Earth's recent history, the Tunguska explosion that took place in Siberia on June 30th, 1908. The idea behind this day to raise public awareness about the asteroid impact hazard and inform the public about the crisis communication actions to be taken at the global level in case of a credible near-Earth object threat. We've decided to take a look at a meteor impact site in greater detail to try and understand how it works. There are multiple such sites in the Indian subcontinent region, including Ramgarh in the southeastern part of Rajasthan. Another is the Dhala crater in Madhya Pradesh and the Lonar Lake in Buldhana district of Maharashtra. We are heading to check out the Lonar Lake in Maharashtra. Lonar Lake is located in the middle of the Deccan Plateau. It was identified in 1823 by the British officer C.J.E. Alexander. This crater was formed 52,000 years ago when a meteor that weighed over 10 lakh tons crashed into the Earth at an estimated speed of 90,000 kilometers per hour. The impact of the crater created a deep depression, about 1.8 kilometers wide and 150 meters deep, before it erupted, spewing molten rock all over. Over time, the jungle took over, and the perennial stream transformed the crater into a tranquil, emerald green lake. Now, how do we know this lake was created because of the impact of a crater? Well, there are several ways. The most compelling is the presence of the substance called masculinite. Now, masculinite is a kind of naturally occurring glass that is only formed by extremely high velocity impacts, and it is found near this lake. The rock here is basaltic, one of the most common rocks in the universe. And there are only 2 meteoric impact sites in the world in this kind of basaltic rock. The other is in Russia. So this is quite unique and can help scientists get information on how impact works in other places in the solar system, like the Moon or Mars.
The shape of the lake, or lunar lake, is a very characteristic and typical. You don't have a completely round lake anywhere else in the whole country or whole world. Why it is important and why it is so characteristic? Because these rocks are very hard, are formed at about 65 million years ago, these volcanic rocks, and one of the lunar lake took place in the Pleistocene time, about 50,000 years ago.
The lake also has many mysteries that surround it. For example, the saline waters of the lake contain microorganisms that are found almost nowhere else on Earth. We can see that it is alkaline since a litmus paper turns blue when dipped in this water. The rocks here have strange magnetic properties. Take this temple that's been made from the local rocks. When a compass is held far away from the rock, it points northwards. But when we hold it closer to the rock, it shifts, clearly affected by the magnetic properties of the rock. Let us see what happens when a meteor hits the Earth's atmosphere. Space is a vacuum, so traveling through space doesn't use too much energy. The meteor in vacuum usually travels at tens of thousands of miles per hour. However, when it hits the Earth's atmosphere, the air in front of it compresses incredibly quickly. When a gas is compressed, its temperature rises. The first couple of layers of the atmosphere, the exosphere and thermosphere, don't have too much air, so the meteors make it through these without too much trouble. But when they hit the mesosphere, there are enough gases to cause friction and create heat. This causes the meteor to heat up so much that it glows. The air burns the meteor until there is nothing left. These are commonly known as shooting stars. Now, sometimes as the Earth is orbiting around the Sun, it passes through debris left over from the disintegration of comets. Although the Earth's orbit around the Sun is almost circular, most comets travel in orbits that are highly elongated ellipses. As a result, some comets have orbits that intersect or partially overlap the Earth's path. When the Earth intersects this orbit in its annual trip, it can run into debris, which burns up on entry into the Earth's atmosphere. Meteor showers associated with particular comet orbits occur at about the same time each year, because it is at those points in the Earth's orbit that the collisions occur. Like the Perseid meteor shower that occurs in August each year because of debris from the comet Swift-Tuttle, or the Orionid meteor shower associated with debris from Halley's Comet that occurs every October. But some meteoroids don't burn up and actually impact the Earth, like in the case of Lunar or Chelyabinsk. These clearly happen when bigger objects enter the Earth's atmosphere, so before they can burn up completely, they reach the ground. And depending on their mass and size, these create craters on the Earth's surface.
Meteorite crater will have a specific shape, usually a oval shaped or round shaped, most of them. It could have to be regular, but it will also have a rim over which, because the rim is formed after the meteor hits the surface.
To explore how this works, we did a small demonstration. We took a dish and filled it with flour. We topped the flour with chocolate to simulate layers of soil. We then took stones of different sizes and dropped in on the surface. If we replay our drip, it is clear that the size and mass of each meteorite changes the size and shape of the crater formed. We now took a similar sized stone and dropped it from a lower height and then a higher height. Clearly, the height from which it falls also defines the scale of the impact. We also see how debris is ejected into the formation of the impact crater, also known as ejecta. By studying the patterns in which lower levels of dirt and rock were tossed up by the impact, scientists can make estimates about how big the meteorite originally was. If we move away from the maida and the stones, here is the science of the fall broken up into 3 bits. There is the compression stage, which is the initial transfer of energy between the meteorite and the Earth. The next stage is known as the excavation stage, where energy vaporizes the meteorite and parts of the ground below it, sending rock vapor miles into the atmosphere. The material thrown up, or ejecta, builds up around the crater, forming what's known as the classic ring. The final modification stage, when some ejecta falls into the crater, partially filling it.
Then there is also another phenomena which takes place after the meteor has hit it, what is called a rebound. So you often get in most of the meteorite craters and rebound hills.
After the break, we explore the way meteor debris can be analyzed to understand what it is made from, and some of the most stunning craters in the world. So keep watching. In our exploration of meteors and asteroids, we head to the Physical Research Laboratory in Ahmedabad, where meteor debris is analyzed to understand its origin and composition. The scientists here are working on samples collected from a meteorite fall that took place on the 6th of June 2017 in Mukundpura in Rajasthan. The process used to analyze samples here is called destructive analysis, where a sample is crushed in a controlled environment and the gases that are trapped in the sample are then analyzed using mass spectrometer. Investigations are done to find out elemental composition and mineralogy of the samples.
If you want to do elemental composition, we have to clean the surface and see that there is no other contamination. And then we have to subject it to an instrument where we do X-ray diffraction or X-ray fluorescence. And then we try to find out the elemental composition, because each element has a unique line in X-rays, and which can be easily identified using X-ray techniques. And we can say this element is present there.
Samples of meteors usually contain minerals like aluminium oxide and magnesium oxide. However, the meteor found in Rajasthan is called the carbonaceous chondrite meteorite. These are very complex meteorites, which are rare, primitive, and contain organic compounds.
Recently, we have come out with the first paper on the Mukundpura rock, which is talking about what is its composition, the basic composition. But much more detailed work is actually going on in the lab, which will be published later on.
The scientists here have more than enough samples to work on, because every day Earth is bombarded with more than 100 tons of dust and sand-sized particles. However, only meteors that are larger than 1 to 2 kilometers could have a large-scale impact on Earth. At 5.4 kilometers in diameter, the largest known potentially hazardous asteroid is Tawatis. By comparison, asteroids that populate the main asteroid belt between Mars and Jupiter and pose no threat to Earth can be as big as 940 kilometers across. Now, when rocks from space actually hit the Earth, they form a crater. Most impact craters are eventually erased due to erosion, vegetation growth, and the movement of the Earth's tectonic plates. But some leave startling evidence, like the enormous meteor crater in Arizona. In 1903, when Daniel Barringer suggested that this was made by the flying space rock, his theory was met with disbelief. Planetary science at that point was not mature enough for geologists to swallow Barringer's impact theory until the 50s and 60s. Another stunning crater is the Vredefort crater in South Africa that is thought to be about 2.02 billion years old. The asteroid that made the crater was estimated to be 6 miles wide, and when it hit the Earth, it made a hole 10 times deeper than the Grand Canyon. The Chicxulub crater is believed to be what's left of the asteroid that killed the dinosaurs. Most of it lies underwater in the Yucatan Peninsula, Mexico. It's approximately 170 kilometers in diameter and is believed to have occurred 6.6 crore years ago. Let's explore a more likely possibility. What happens if a space rock hits a satellite? In 1993, the European communications satellite Olympus was hit by a meteoroid associated with the Perseid meteor shower. This hit Olympus's electronics bay, destroying the device that controlled the spacecraft's momentum. By the time engineers were able to get the tumbling spacecraft under control, its fuel was exhausted and the mission had to be scrapped. Many satellites and even the International Space Station have been hit with micrometeoroids, which are tiny particles from meteoroids. Now, the ISS has a shield that can resist hypervelocity impact of particles up to a certain size, that is, nearly a millimeter. These are called MMOD shield, micro, meteoroid, and orbital debris. It has 2 layers. If the first layer is penetrated and broken, it doesn't stop the particle, but it breaks it. Actually, the particle even vaporizes because of the heat released during the impact. The fragments expand and impact the second layer over a much larger area, so it's much easier to resist. Next up, the NASA Observation Program, dedicated to tracking near-Earth objects, followed by an analysis of which asteroids pose a threat to our planet. And what are the ways science can be used to actually move the asteroid if so needed? Keep watching to find out. NASA's Near-Earth Object Observations Program is responsible for finding, tracking, and characterizing near-Earth objects. The program is a key element of the agency's Planetary Defense Coordination Office. Let's study some of these in more detail to see if they pose a threat to us. In 2013, a small asteroid called 2012 DA14 passed very close to the Earth. So close that it passed inside the ring of a geosynchronous weather and communication satellite. In 2017, Florence, one of the largest near-Earth asteroids, passed by. It was almost 4.8 kilometers wide and passes about 70 lakh kilometers from Earth. This sounds like a lot, but that's a pretty close pass when we think about the vastness of space. One part of NASA's program, called NEA Scout, basically scouts out near-Earth asteroids. This is a robotic reconnaissance mission that maps the trajectory of recently discovered asteroids to see if they could crash into Earth. This came into effect in 2017-2018, but has the capacity of detecting possible impacts like the one that happened at Chelyabinsk.
What Scout program did was it predicted that there is going to be a small asteroid which is going to crash at Botswana in Africa. And indeed, in June this year, this asteroid crashed into Botswana region.
Now, what happens if a larger, more dangerous asteroid is on a collision course with Earth? Over the next decade, NASA will develop and test ways in which an asteroid headed our way can be deflected and destroyed. There are 3 techniques that could be used depending on the size of an incoming asteroid and the amount of warning time we have before it hits. One is a gravity tractor, a heavy spacecraft that hovers near the asteroid so that its gravity can tug on the asteroid and pull it off its course. Another plan is to use a kinetic impactor which deliberately crashes a spacecraft into the asteroid to change its speed and orbit. A nuclear device could also be used against an incoming asteroid to either deflect it or break it up into pieces small enough that they burn up in Earth's atmosphere.
Yes, you could do nuclear explosion like the movie, but these are very expensive and they have to be done in a very accurate manner. If there is a miss, then the nuclear disaster can be very, very lethal.
Whatever the solutions to an asteroid's impact, it is clear that understanding and tracking them is critical. There is a chance that an asteroid could hit Earth and destroy entire species, huge regions, and even the planet itself. The hope is that science can develop to an extent to prevent another collision at this scale.